Hello friends, welcome to my lecture on review of bilateral Z transforms. The two-sided Z transform of a sequence by n is defined as Z by n equal to sigma n equal to minus infinity to infinity y n Z to the power minus n, and this is defined for those values of Z for which the series on the right side is convergent. The values of Z for which the sum on the right side converges is called the region of convergence of Z by n, or simply the ROCY. ROCY means region of convergence for by Z. This is by Z. Z of by n is by Z. As with the unilateral Z transform, the two-sided Z transform is again a complex function of a complex variable. Z is a complex variable, and when we take the Z transform, we get again a complex number. So, let us consider the following sequence. By n is equal to a to the power n u n plus b n u to the u minus n minus 1. We know that u n is defined as 1 when n is greater than or equal to 0 and 0 elsewhere. Okay. So, here when n is greater than or equal to 0, we get by n as a to the power n, and when n is less than 0, okay, n is less than 0, then what will happen? U minus n minus 1. Say n is less than 0 means n is taking values minus 1, minus 2 and so on. N is less than 0 means n is less than or equal to minus 1. So, we can say that minus 1 minus n is greater than or equal to 0. So, when minus 1 minus n is greater than or equal to 0 means n is less than or equal to minus n. So, when n is less than or equal to minus 1, u minus n minus 1 will be equal to 1, and this u n will be 0. So, by n will be b to the power n. Okay. So, by n is equal to a to the power n when n is greater than or equal to 0, b to the power n when n is less than 0. Now, let us take the Z transform of the sequence by n. So, Z transform by n is sigma n equal to minus infinity to infinity a n u n plus b n u minus n minus 1 Z to the power minus n. Now, when n is greater than or equal to 0, u n is 1. So, this is sigma 0 to infinity a n Z to the power minus n, and when n is less than or equal to minus 1, u n is 0, u minus n minus 1 is 1. So, minus infinity to minus 1 b to the power n Z to the power minus n. Now, we know that sigma n equal to 0 to infinity a to the power n Z to the power minus n. This is the Z transform of a to the power n. This is n equal to 0 to infinity a by Z to the power n. So, this is equal to Z over Z minus a, because it is a geometric series 1 over 1 minus a by Z, provided mod of Z is greater than mod of a. Here we have sigma n equal to minus infinity to minus 1 b n Z to the power minus n. Okay. We can also express this as sigma 1 to infinity replacing n by minus n, b to the power minus n Z to the power n. Okay. So, that this is equal to sigma 1 to infinity Z by b to the power n. Okay. This is again a geometric series and will be convergent if mod of Z over b is less than 1. Okay. Sigma n equal to 1 to infinity Z over b raised to the power n is Z over b over 1 minus Z over b, provided mod of Z is less than mod of b. So, this is Z over b minus Z. Okay. So, if mod of a is less than mod of Z, then we have Z over Z minus a. If mod of Z is less than mod of b, then we have the sum of the other series Z over b minus Z. So, both the series are convergent in the annular region given by mod of Z greater than mod of a, but less than mod of b. Now, so we can say that Z transform of the y n sequence is Z over Z minus a plus Z over b minus Z, where mod of a is less than mod of Z less than mod of b. The region of convergence of the sequence by n of the by Z transform of y n is given by ROCY, and ROCY here is a ring, or we can call it a annular region in the complex plane as shown here. You see we have mod of A less than mod of Z. So, this R minus is mod of A and R plus is mod of B. Okay. So, taking R minus as mod of A, R plus as mod of B, we see that region of convergence lies between two concentric circles. One is mod of Z equal to mod of A, and the other one is mod of Z equal to mod of B. Now, R minus you see we have seen that R minus is determined by n when n is greater than or equal to 0. Okay. This is R minus. Okay. R minus is determined by this sequence. Okay. This series. Okay. R plus is determined by this one. Okay. So, R minus is determined by n when n is greater than or equal to 0, R plus is determined by n when n is less than 0. If n equal to 0 for n less than 0, suppose we take n equal to 0 for n less than 0, then what will happen? N equal to 0 for n less than 0 we take, that means we will only have n equal to a to the power n when n is greater than or equal to 0, and then the region of convergence will be mod of Z greater than mod of A, because this part will vanish. Okay. So, we will have when n is 0 for n less than 0, then we have Z n equal to this. Okay, and R plus is infinity. So, we have the region of convergence as mod Z greater than mod of A, that is outside of the circular disc, mod of Z equal to mod of less than or equal to mod of A. This is the circular disc which center at origin radius mod of A. So, the region outside this circular disc will be the region of convergence, and which is actually the one sided Z transform. Now, consequently the region of convergence corresponds to mod of Z greater than R minus as shown in this figure. Now, if yn is equal to 0 for n less greater than 0, okay, then we will have Zy n equal to minus infinity to minus 1 or you can say minus infinity to 0 by n Z to the power minus n, okay, and R minus then will be 0, okay, R minus will be equal to 0. So, this will be this one, this region, okay, the region is mod of Z less than B. Okay. So, mod of Z less than B means circular disc. So, when n is 0 for n greater than 0, then we have Zy n equal to sigma n equal to minus infinity to 0 by n Z to the power minus n, and the region of convergence will be mod of Z less than mod of B, that is the circular disc, this circular disc. Okay. Region of convergence corresponds to a solid disc in the complex plane, that is we have mod of Z less than R plus. Okay, R plus is mod of B. Now, thus the two sided Z transform can accommodate a wider range of signal behaviors, since they can be left sided, right sided or two sided and still have a bilateral Z transform. Now, let us say the Z transform of a sequence x n n equal to minus infinity to infinity be given by x z equal to b z over a z, where z belongs to ROCX, region of convergence of x z. Then the zeros and poles of x z are given by the sets zeros of x z, this x z are given by the set of all z such that b z equal to 0, and the poles of x z are given by the set z set of all z such that a z equal to 0. In the case of a rational Z transform, the ROC is always bounded by poles. Okay. Therefore, ROC is either a disc or an annulus or the entire plane minus a disc, with the possible exclusion of 0 and infinity. Now, let us consider the by z equal to z over z minus 1. So, you can see by z over z by z equal to z over z minus 1 has a pole at z equal to 1, and the region of convergence is mod of z greater than 1. It corresponds to the sequence, you know that z over z minus 1 is the Z transform of UN sequence, that is 1 to the power n. Z transform of 1 to the power n is z over z minus 1, okay, and 1 to the power n is also written as UN. Because UN is equal to 1 for all n greater than or equal to 0 and 0 otherwise. Okay. So, Z transform of 1 to the power n, or also we write Z transform of 1. Okay. So, this is the Z transform of the sequence un n greater than or equal to 0. The region of convergence for the Z transform is given by mod of Z greater than 1. Okay. The region outside this circle mod Z equal to 1, and you can see this region is bounded by this circle which has got a pole, the pole at Z equal to 1. Okay. So, what we have said here was the region of convergence is either a disk or an annulus or the entire plane minus a disk. So, here the region of convergence is the entire plane minus this disk mod of Z less than or equal to 1, and we have also seen that region of convergence bounded by poles. You can see the pole is occurring here on the boundary of the region of convergence. Now, rational transform by Z equal to Z over Z minus 2 when mod of Z is less than 2. Okay, let us take this one. So, here we have a pole at Z equal to 2. You can see by Z equal to Z over Z minus 2, and you can see here mod of Z is less than 2. It means that the region of convergence is a solid disk. Okay, region of convergence is a solid disk means this case will occur when your by n is 0 for n greater than 0. Okay. So, let us say what is the sequence y n in this case? We can write it as we have mod of Z over 2 less than 1. Okay. So, this means that I will write it as Z over minus 2 times 1 minus Z over 2. Okay. Then this will be minus Z upon 2 sigma n equal to 0 to infinity minus Z by 2. So, we get Z by 2 raised to the power n. Okay. So, this will be equal to minus sigma n equal to 0 to infinity Z to the power n plus 1 divided by 2 to the power n plus 1. Okay. So, this we can say this is nothing but sigma minus sigma n equal to 1 to infinity Z to the power n divided by 2 to the power n, or I can write it as by Z equal to minus sigma n equal to minus infinity to minus 1 Z to the power replacing n by minus n. Okay. So, Z to the power minus n 2 to the power minus n, and we get minus sigma n equal to minus infinity to minus 1 2 to the power n Z to the power minus n. Okay. So, by n is you see minus 2 raised to the power 10 when n is less than or equal to minus 1. Okay. And this is this can also be expressed as n less than or equal to minus 1 can be replaced by this expression by n equal to minus 2 raised to the power n u minus n minus 1. Okay. When you have u minus n minus 1, it will have value 1 when n is less than or equal to minus 1. So, this condition on n that n is less than or equal to minus 1 can be replaced by taking u minus n minus 1 together with minus 2 raised to the power minus n. So, this is the sequence here. Region of convergence you can see is the disk, this disk mod Z less than 2, and its boundary has a pole at Z equal to 2. Now, consider the sequence with rational transform by Z equal to Z over Z minus 2 whole square when mod of Z is less than 2. We can see that it has a pole of order 2 at Z equal to 2. Okay. And we know that Z transform of a to the power n is Z over Z minus a. Okay. In case mod of Z is greater than mod of a. Okay. And then we know that Z transform of n a to the power n is equal to a z divided by Z minus a whole square when mod of Z is greater than mod of a. Okay. So, here again we can easily show that Z transform of we have seen earlier, we have seen that Z transform of the sequence by n, okay, which is minus 2 raised to the power minus n, okay, is Z over Z minus 2, okay, when n is less than or equal to minus 1. This can be here 2 can be replaced by a. So, we can easily see that Z transform of Z minus a raised to the power n is Z over Z minus a when mod of Z is less than mod of a. Okay. In a similar manner as we have done in the previous case, okay, these by following same steps we can see that Z transform of minus a to the power n is Z over Z minus a and n is less than or equal to minus 1. Okay. So, then Z transform of n into a to the power n, this is minus a z divided by z minus a. Okay. So, Z transform of n a to the power n is again can be obtained by differentiating this, and we get Z transform of n a to the power n equal to this is Z transform of a to the power n. Z transform of a to the power n we can write as minus z over z minus a, and then Z transform of n a to the power n is equal to minus a z over z minus a whole square when n is less than or equal to minus 1. It can be again found by using the recurrence relation as we have used earlier. We know the recurrence relation, if d over dz if z minus z times d over dz of by z is equal to minus z d over dz of by z equal to suppose by z is the Z transform of a to the power n. Okay. Then Z transform of, suppose we know the Z transform of by n, Z transform of by n we know, suppose Z transform by n is sigma n equal to 0 to infinity by n z to the power minus n. Then Z transform d over dz of, let us say this is by z, this is by z, then d over dz of by z equal to sigma n equal to 0 to infinity by n into minus n z to the power minus n minus 1. Okay. So, we multiply by minus z, then minus z d over dz of by z equal to z trans is equal to sigma n equal to 0 to infinity n by n into z to the power minus n. So, we get Z transform of n by n. Okay. So, Z transform of n by n, if we know the Z transform of by n, Z transform of n by n can be obtained by differentiating by z with respect to z and then multiplying by minus z. So, this formula holds for n greater than or equal to 0. This formula can also will also be applicable when n is less than or equal to minus 1. So, here if you have z of a to the power n equal to minus z over z minus a, when you multiply a to the power n by n, we differentiate this with respect to z and then multiply by minus z. Let us see d over dz of minus z divided by z minus a. This will give you derivative of numerator is minus 1 into z minus a, derivative denominator is 1. So, minus z divided by z minus a whole square, and what we will get minus z plus a minus plus z divided by z minus a whole square, and we will get a over z minus a whole square. Okay. So, we multiply by minus z d over dz of minus z divided by z minus a, and what we get? We get minus az divided by z minus a whole square. Okay. So, this is z transform of n a to the power n minus az upon z minus a whole square. So, since n a to the power n u minus n minus 1 goes to minus az by z minus a whole square when mod of z is less than a, thus we have y n equal to. So, we can see y n from here. Okay. We have z over z minus 2 whole square. So, replace a by 2 here. Okay. So, we have n 2 to the power n u minus n minus 1 with minus divided by minus 2. Okay. So, we will have n 2 to the power n u minus n minus 1 divided by minus, we can say minus 1 over 2. Okay. This is nothing but the inverse Z transform of Z over Z minus 2 whole square. Okay. So, inverse Z transform of this is given by this expression. Okay. Now, let us say two sequences x n by n have two sided Z transforms as Z x n and Z y n respectively, then the superposition of these sequences will also have two sided Z transform, so long as Z x n Z y n are jointly defined on a null subset of the Z plane. If suppose I write W n sequence as A x n plus B y n, then Z w n equal to A z x n plus B z y n. Okay. And ROC W will contain ROC x intersection ROC y. That means, ROC W, the region of convergence of the Z transform of the sequence W n will be at least as large as the intersection of ROC x and ROC y. So, this is the theorem. We can easily prove this theorem using the definition of Z transform. And here let us consider W n equal to x n plus by n. Z x n suppose is W Z over Z plus 2 Z plus 3, where mod of Z is less than 2. Z y n is 2 over Z plus 2, where mod of Z is less than 2. Okay. So, then from this what do you notice? W n is equal to x n plus y n. Okay. So, W n equal to Z transform of W n equal to Z transform of x n plus Z transform of y n, and this will be equal to Z plus 2 over Z plus 2 Z plus 3 plus 2 over Z plus 2. Okay. So, what we get? Z plus 2 Z plus 3, and what we get here? Z here, and Z plus 2 2 times Z plus 3. So, what you get? 2 Z plus 6, that is 3 Z plus 6. So, 3 times Z plus 2 divided by Z plus 2 Z plus 3. Okay. So, this will cancel and we get 3 over Z plus 3. Now, you can see the region of convergence here is mod Z less than 2, here mod Z less than 2. Okay. What is the region of convergence here we will get? Because it has a pole at Z equal to minus 3. Okay. So, there is a pole at Z equal to minus 3, ROC x intersection ROC y. Okay. ROC x intersection ROC y is the same. Okay, because they are same, mod of Z less than 2, mod of Z less than 2. So, this is Z of all Z such that mod of Z is less than 2, and ROC W is what? 3 over Z plus 3. So, this is because it has a pole. So, ROC W will be the boundary will have a bounded by this pole Z equal to minus 3. So, this is mod of Z less than 3. Okay. So, mod of Z less than 3 is, you can see we know that ROC W contains ROC x intersection ROC y. Okay. So, it is mod of Z less than 3, and mod of Z less than 3 contains mod of Z less than 2. Okay. So, it is at least as big as the intersection of ROC x intersection ROC y. Now, for the two sided Z transform, the shifting properties are much simpler than their counterparts in the unilateral Z transform, since we do not need to worry about the terms shifting into or out of the summation defining the Z transform. Let us say we simply have here x n goes to Z x n, implied by x n minus k goes to Z to the power minus k Z x n, and the region of convergence of the shifted sequence remains unchanged except for the possible addition or deletion of Z equal to 0 or mod of z equal to infinity. So, if xn goes to zxn, then the shifted sequence xn minus k will have z transform z to the power minus k zxn. Now, the convolution property for the two sided Z transform follows in a similar manner as in the case of unilateral Z transform. We have if we have two sequences Hn and Xn, then their convolution is defined as by n equal to sigma m equal to minus infinity to infinity Hm Xn minus m. Then their Z transform of by n is product of the Z transform of Hn and Xn. Okay. And the region of convergence of y, okay, by z will contain at least as large as the region of intersection of region of convergence of x intersection region of convergence of h. Okay. So, so long as there exists a non-null intersection, okay, so long as there exists a non-null intersection ROCX intersection ROCH, just as with linearity, if there is a pole 0 cancellation or on a boundary of the intersection, then the ROCY expands to the next pole. Suppose it happens that we have a pole in the we have a 0 in the numerator, say z at z equal to a, in the denominator also we have a pole at z equal to a. So, then they will cancel, okay. Just as in the if there is a pole 0 cancellation on a boundary of the intersection, then ROC expands to the next pole. Just say for example, here we have seen that z plus 2 got cancelled and we move to the next pole, okay. So, if there is a pole 0 cancellation on a boundary of the intersection, then ROCY expands to the next pole. Here we had at the intersection of ROCX ROCY was the same z such that mod of z less than 2, and we cancelled this z plus 2 factor here, okay. So, the such a situation if it occurs, okay, then if there is a pole 0 cancellation on the boundary on a boundary of the intersection, then ROCY expands to the next pole as in the previous case. So, we have by n equal to sigma m equal to minus infinity to infinity Hm Xn minus m, then z by n, okay, z transform of by n by definition of bilateral Z transform is sigma n equal to minus infinity to infinity, okay, this by n z to the power minus n, and this can be then written as sigma m equal to minus infinity to infinity Hm sigma n equal to minus infinity to infinity Xn minus m z minus n, okay. And then this is sigma m equal to minus infinity to infinity Hm z to the power, you can write it as z to the power minus m it should be. So, this is z to the power minus n can be written as z to the power minus n minus m and then z to the power minus m, okay. So, here we will have sigma m equal to minus, so this will be actually this will be equal to sigma m equal to minus infinity to infinity Hm z to the power minus m and then sigma n equal to minus infinity to infinity Xn minus m z minus n minus m, okay. So, this becomes your zxn, okay, and this becomes zhn, okay. So, zhn is equal to this is equal to zhn into zxn. So, this z to the power minus n will be written as z to the power minus n minus m into z to the power minus m, and we get the result. So, this is the convolution theorem for the bilateral Z transform. Now, consider the sequences Xn and Hn for which the Z transforms are Zxn, Zhn respectively. Zhn is 1 over Z plus 1 Z plus 2 and the region of convergence is 1 less than mod Z less than 2. Zxn is Z plus 1 over Z plus 2, the region of convergence is mod Z less than 2. Let us define by n z by n equal to zhn into zxn. Now, ROCX into intersection ROCH, okay, is you can see here this is the annular this okay, this is mod z equal to 1, this is mod z equal to 2, this is mod z equal to 1, this is mod z equal to 2, okay. Then here we have annular region, okay, this is annular region, this one, and here we have mod z less than 2, that means complete disk. So, intersection when you take, we will get the annular region. So, the ROC x intersection ROC h is equal to this, which is a non-null set, and ROC y is what? ROC y is ZHN into ZXN. ZHN into ZXN is how much? 1 over Z plus 1 into Z plus 2, and we get Z plus 1 here over Z plus 2. Okay, now you can see Z equal to minus 1 is a 0 of ZYN, okay, and Z equal to minus 1 is also a pole of Z equal to is also a pole of ZYN, and we, so in the case of the cancellation of 0 and pole, okay, we move to the next pole. So, here we get 1 over Z plus 2 whole square. So, we now have a pole of order 2 at Z equal to minus 2. So, we move to this mod of Z equal to 2, and therefore, the region of convergence is Z such that mod of Z less than 2. Okay. So, this is what we had said here. Here if there is a pole 0 cancellation on a boundary of the intersection, okay, then ROCY expands to the next pole. Okay. So, that is what we have to say in this lecture. Thank you very much for your attention.